Starting off our final session for the day, Colin DeGraf.
Okay, can you hear me? Okay, so yes, if you don't know me, I'm Colin DeGraf. So thanks everybody for coming. It's nice to have an in-person conference again and to see so many familiar faces as well as new ones. So I'm sort of changing directions a bit. I'm going to focus on supermassive black holes. So specifically, I'm going to talk about mostly mergers. If you want to talk about formation, growth, all that, I'd be very happy to, but I won't do it in this talk. So I'll talk about rates of black hole mergers, look at how they connect to their host galaxies, and then also point out how the time scale between when simulations very often merge black holes and when they should really merge is quite important, and really we need to keep doing better and better with that. So I'm sure everyone is familiar with the LIGO detection, which I keep thinking of as sort of recent, but is almost 7 years old now. So this is the original LIGO detection, and then of course when that happened, it made news all over. So lots of people have heard about it, and it's great science and everything, but my primary interest is supermassive black holes, and LIGO won't really help with that. But LISA will. We've got a little bit until that happens, but it should give us some really good data once it launches. And we also have pulsar timing arrays, where we have some currently running. So if you're not familiar with pulsar timing arrays, you're basically looking at pulsars and using the signal from those pulsars as your baseline for an interferometer. So both LISA and pulsar timing arrays should be able to detect supermassive black hole mergers through gravitational waves, similar to how LIGO did. Hasn't happened yet, so it's very important that we look into that and do our best to model all of these mergers. So that's one of the things I've been looking at a lot. So the first part of this talk I'm going to discuss using the Illustris and TNG simulations. I am not going to go into a lot of detail about that right now. The simulations themselves, I think they're used enough. Most people are at least broadly familiar with them. But they're full cosmological simulations run with a moving mesh code, a repo. You've got star formation, stellar feedback, stellar winds, gas cooling, and there's actually a set of simulations, so ranging from 50 to 300 megaparsecs on a side to the simulation volume. So we've got higher resolution ones and larger volume ones, so we can get a good range of things where we need the high resolution, and rare objects where we want good statistics, we've got the larger volumes. And if you aren't familiar, all of these images are coming from the I think these are all from Illustris simulations, but I'm also going to look at TNG some. So I said we want to look at the black hole mergers. So the first thing is to check what kind of galaxies are these mergers taking place in. So what I've plotted here are contours of the black hole mass, stellar mass relation of galaxies. So that's the colored contours. And then all of the dots represent supermassive black hole mergers in the simulation. So this is all right around redshift 0.5. So we can see, first of all, they are tending to take place in representative galaxies. They're not generally overmassive or undermassive in either the black hole or the galaxy. There are a few unusual cases, but for the most part, they're quite representative. I've also shown in blue here, those are primarily mergers that would be detectable by LISA. And in red are mergers that would be more detectable by pulsar timing arrays. So this has to do with just the wavelength of the gravitational waves. So pulsar timing arrays are the ones that will be sensitive to the very high end. So we've got a good probe of black hole galaxy properties when we start detecting these mergers. And between LISA and pulsar timing arrays, we should really span sort of the full range of galaxies. We've got a full range of galaxy scales. So it's very promising for what should be coming. So the other thing we want to consider is, what do those galaxies look like? So this is all at redshift 0.5. So if you just look at the right-hand panel for a second, those are the mergers from redshift 0.5. These are major black hole mergers. I'm not selecting galaxy mergers. This is just galaxies which host a major black hole merger around redshift 0.5. And so that's what all of these are showing. And then I did the same thing at redshift 2 here. And I've done it at other redshifts. I'm just not putting them all up. So, I mean, you can see some nice things like the nice color difference going from blue to red as you get to later times in the universe. But the other thing is just at a glance, you can immediately see these are disturbed galaxies. Now, at a glance, you can't tell that every single one is. But for the most part, you can look and you see lots of different morphologies that you can see evidence that there's been some sort of recent galaxy merger. And again, this is just selecting based on the fact that there's a black hole merger, not a galaxy merger. Now, it's worth pointing out, because of the way the simulations work, that's sort of cheating a little bit, because this is using Illustris and TNG. They only seed one black hole per galaxy. And so the only way to get a black hole merger is to merge two galaxies together. But we're probing when the black holes merge, not when the galaxies merge. And we can see here that there is morphological evidence of that galaxy merger. So here you can see, this is from Illustris. This is one galaxy, well, with a second galaxy that comes in and merges. But this is, each image is just a different time. And so 0 mega years is when the two black holes merge. And so you can see before the black hole merger, you've just got a galaxy. Just before the black hole merger, you can see sort of what looks like a bit of an incoming galaxy. And then a very clearly disturbed galaxy, which eventually starts relaxing again. So the morphological evidence in the host galaxy survives for hundreds of mega years. This is another example. This one's from the TNG simulation. Same idea, where you've got a nice isolated galaxy at first. You can then see between these two snapshots, there was a galaxy merger and a black hole merger, and now it's a disturbed galaxy. So again, we see morphological evidence of the disturbance. It's a little hard to see on the projector, but you can also see light shells. That's also more merger evidence at later times. So that's sort of looking at individual cases, but what we wanted to do is get quantitative statistics and see how frequent is it that we can really look at this and tell they're disturbed. So as a first estimate, use the Gini M20 relation. So for the sake of time, I won't go into details a lot here, but it's an approximation, and we're saying things above this gray line show morphology that would be more consistent with a galaxy merger. Below it is not. And the contours here are galaxies in Illustris. So you can see there are, if you look at the actual statistics, there are more that are non-merger morphologies than merger morphologies here. But then we look at the galaxies that are hosting supermassive black hole mergers. And that's what these data points show. So the black data points are for just if a galaxy hosts a supermassive black hole merger. And you can see it pretty much follows the underlying galaxy properties. The blue data points is saying, well, we'll limit ourselves to only major black hole mergers, which we define as saying the mass ratio is 4:1, but the mass ratio of the black holes. And there you start getting slightly above, but not by much. In red, however, we're limited to major black hole mergers, and the black holes have to be massive, which in this case we're defining as above 10 to the 7 solar masses. And there you can see very clearly well above that relation, this sort of criteria for defining a galaxy merger. So to show this in another way, we can just define the quantity, how much above that or below that relation is it. We'll call that S. And then plot the S parameter against how long it has been since the black hole merger occurs. So anything to the right of the green line shows morphological evidence of a galaxy merger, and to the left does not. And we're curious to see how long does that morphological evidence survive after the merger takes place. So if we put that on, you can see among the high mass major black hole mergers, the red points here, it survives for several hundred mega years. But anything longer ago than that, and the galaxy has had time to relax again, and you no longer see evidence for the merger. So it's really only the first couple hundred mega years after the black hole merger that we keep the information. The problem is, that's only a couple hundred mega years from when the simulation merged the black holes. And that's not an accurate time. So this was looking at Illustris. What I just showed was Illustris. I've also looked at similar things for TNG. And the issue is, when a black hole enters a galaxy from a galaxy merger, the movement of the black hole from the outskirts of the larger galaxy into the center is not physical. So it's recentered towards the potential minimum. So the time it takes to move to the center of the galaxy is often too fast, because it's not physically motivated, physically modeled anyway. And it ignores the fact that once you get the two black holes close together, they'll form a binary, and the actual coalescence time can be long. So the actual merger of the black holes should be much later than when the simulation has the two particles merge. So there's been a lot of work looking into this. This is some plots from a paper by Luke Kelly, sort of looking at the hardening timescale for binary black holes. And it's dependent on their initial separation and the eccentricity of the orbit. But you can see the hardening timescales can last into gigayears or even tens of gigayears or longer. In addition, you have the actual infall time to go from the outskirts of the galaxy into the center. And so this is a plot from a paper by Marta Voluntari, who was looking at the Horizon AGN simulations and calculated, well, because that was also doing recentering of the black holes. So they calculate using dynamical friction models. You can estimate approximately how long should it have taken, based on the galaxy properties, for the black hole to migrate into the center of the galaxy. And mostly you can just look at this top left panel, because that's the dynamical friction time, which in most cases is the dominant factor from what she found. And there you can see tens of gigayears, even 1,000 gigayears is potentially possible. Now, this is based on an instantaneous galaxy property and saying, okay, if we make some assumptions about the density profile of the galaxy and none of it changes, how long would it take for the black hole to get to the center based only on dynamical friction? So in reality, it should go faster than that. But it could be an extremely long period of time. So that several hundred mega years that the galaxy looks disturbed is not good enough. So if we detect black hole mergers with LISA or pulsar timing array, and then we try and look for the disturbed galaxy, it should be too late. The galaxy will have relaxed already. Should still be fascinating to look at the galaxy, but we don't expect it to be a clearly disturbed morphology anymore. So we wanted to look at that in a little more detail. So this is 6 different undergraduates who I worked with. And they did something similar to what Marta did, and took all of the mergers in Illustris, looked at when they merged, looked at the galaxies they were in, calculated an estimated dynamical friction-based infall time, and said, okay, so now let's delay every merger by the amount that the dynamical friction would predict it should have taken to fall in. And that means if the merger happens later, the black holes will have grown more. So when they finally do merge, they'll be more massive. So they also calculated how much bigger those black holes should have been when the merger finally took place. Produced a whole new catalog. So you can see down here in blue, the blue contours, that's showing original Illustris data. So the merger mass at the bottom and redshift here. And then in red is after they impose this delay time from calculating the dynamical friction. And so you can see it's sort of everything from up here starts shifting down and to the right. So the mergers are happening later, and the mergers are more massive when they do occur. So there's a paper looking into this in a lot more detail. I'll talk about it a little bit, but you can look at a lot more information if you pull up the paper. So basic idea is we looked at the expected rate at which gravitational waves would reach the Earth. So how many would we find per year coming from a certain redshift? And so based on the Illustris simulation, we get this curve. And then so I said they calculated dynamical friction delays. But as a first test, they also just said, okay, let's just look at 500 or 1,000 mega-year delays. So if everything is delayed by the same amount, the mergers, instead of being here, just get shifted to later in time. Makes perfect sense. Then we limited ourselves to only look at mergers that LISA may be able to detect. And so that then drops the rate down a lot because many of the mergers are not detectable by LISA. They're too massive. So you can see that including this delay time, we're significantly decreasing the number of mergers that LISA might be able to detect. However, this is strongly seed dependent because Illustris seeds black holes at already the high end of what LISA can detect. So if we included lower masses, we would get more, and I'll talk about that more shortly. But what starts getting quite interesting is these dotted lines are now high mass mergers that might be detectable with pulsar timing arrays. And what's particularly interesting is this black line is without any time delay. And as you increase the time delay for the merger to happen, we actually start getting more mergers that could be detected by pulsar timing arrays. And that's because we're waiting until later times, and the black holes have more time to grow, so we end up with more high mass mergers that may be PTA detectable. So that was a great project and really showed how important these delay times are and modeling it more accurately. Now I'm going to talk about a different simulation that actually incorporates dynamical friction directly. So this is called the Astrid simulation. There are several different papers you can look up to see some galaxy property and black hole properties from this simulation. I'm not going to go through all the details of the simulation, but the black hole is what's particularly relevant here, so I'll discuss that briefly. So first of all, one big change is the seed mass. So instead of doing something like Illustris or TNG, where the black holes are seeded above 10 to the 6 solar masses, here the black holes are seeded from a power law distribution ranging from 3 times 10 to the 4 to 3 times 10 to the 5 solar masses. So we've got 1 to 2 orders of magnitude lower mass black holes. We also include dynamical friction. This is similar to some of Michael Tremel's work in the Romulus simulations, if you're familiar with those. So this is actually modeling how the black holes fall in towards the center of the galaxy. And because the dynamical friction means we're modeling the velocities of these black holes accurately, instead of merging black holes as soon as they get close together, they'll only get merged if the pair of black holes are gravitationally bound when they're close together. So it is possible to have flybys, and in fact repeated flybys in many cases, before the final merger occurs. So just a couple quick plots to show you sort of the simulation seems to be doing pretty well. So this is the X-ray luminosity function. So the lines are from the Astrid simulation, and the data points are observational data. So you can see this is quite good. You may notice this only goes down to redshift 3. Simulation's still being run. We've actually reached redshift, a little below redshift 2 now, but what I'm going to talk about will mostly just be limited to redshift 3 and above for the moment. Here you can see black hole mass, galaxy mass relation. And again, if you compare observational data to the simulation, it's doing a good job. So the simulation overall is producing what we would broadly expect. In addition, like I said, we've got the actual motion of the black holes. Here is just a whole bunch of examples of orbital trajectories of these black holes as they spiral in towards the center. To give you a slightly more concrete set of examples, each row here is a separate case. And so you can see this is at redshift 5, and then slightly lower redshift, and you can see the trajectory from each step to the next. So you can see some that do end up with a pretty circular orbit towards the end, some that have a pretty circular orbit for quite a long time. There's a wide range of different orbital behaviors that we have. So we can use all of that to then look at what we get out of the simulation. So the first thing is black hole mass function. And so here I compare to TNG 300, which I'll pretty much do for the rest of this talk. So in red is the Astrid simulation, and in blue is TNG 300. So you can see, compare the dashed lines and the dotted lines, very good agreement. As you start getting to lower redshift, you can see that TNG starts to get this sort of flattened bit that bumps above Astrid. So TNG is growing the larger black holes a bit more efficiently as you get to later times. So that is one difference to have. And of course, all of this is very different as well. So that left-hand side, to see that a little bit more clearly, this is the same thing, but I'm now only showing redshift 5, so we can just see it a little more clearly. And you can see the seed mass, right? So TNG seeds just above 10 to the 6 solar masses. So you've got this big spike in the mass function. Astrid does a power law distribution. That's why this has a slope of -1. So we've got lower seed masses, and it's also not a single mass, but a nice power law there. But otherwise, they agree quite nicely. But I really want to push into the mergers. So I've also plotted the merger mass function. So this is a mass function of black hole masses, but based on the black hole mergers which happen within 75 megayears of, in this case, redshift 5. Actually, this one might have been 100 megayears at high redshift, but lower redshift I use 75 megayears. And so here you can see the masses of merging black holes is pretty comparable between TNG and Astrid. But Astrid is pushing to much lower masses as well. So we can look at this at different redshifts. So this was the same redshift 5, 4, 3. At redshift 3, there's that bump that I mentioned from TNG growing a bit more efficiently. And if you look at the merger masses, you see that same bump. So what's nice to get from this is if you look at the ratio between the solid line and the dashed line, that's basically telling you the rate at which mergers occur for a given black hole mass. And if we plot that, so what's being plotted here is now for a black hole of 10 to the 7 solar masses, how many mergers do you expect to get per gigayear? And you can see between the two simulations, they agree shockingly well. Now, we expect them to agree pretty well because it's largely based on galaxy merger rates. But also remember, TNG did not have dynamical friction and Astrid does. And so even though once you're including this, the dynamical friction times are significant, but not so significant that it drastically changes the rate at which an individual black hole will tend to merge. But again, you see Astrid extends to much lower masses. So we're able to get a lot more mergers, because even though these are rarer mergers per individual black hole, as we saw in the mass function, way more low mass black holes than high mass black holes. So actually, this tends to be the majority of mergers. So we can see that explicitly. This is the same thing I talked about before, sort of the rate at which gravitational waves from black hole mergers will reach Earth. So it includes integrating over cosmic volume. And these colored lines are Illustris and TNG simulations. And they all agree quite well. There's some resolution differences. What was that?
Vertical axis isn't it?
Yeah, I see that. So, not sure exactly what happened. It ends up being rates close to, depends on which one you use, but 1 to a few per year. And this is at this redshift, right? So it's dz dt. So as you push to lower redshifts, like I said, this one's sorry, that says Asterix. That was the old name of the simulation. But so Astrid was run to redshift 3 at this point. So what we see is Astrid has a lot more mergers than the TNG and Illustris suite of simulations. So that's because we have these lower mass seeds. They're being seeded in lower mass galaxies. We have a lot more of them. If we limit mergers to only mergers where both merging black holes are above the TNG seed mass, then we get this dashed line. So then we can see there's a big difference between the two. And of course, the dashed line is actually below this because a lot of what gets seeded in TNG at 10 to the 6, we're seeding at a lower mass, and so it gets cut out until it's had time to grow a bit. So you can see that clearly here. So this is now just a 2D distribution merger redshift and the mass of the more massive black hole involved in the merger. And above the seed mass for TNG, these look very similar to each other. But where TNG has this sort of very large number of mergers all close to the seed mass, Astrid has now spread that out across a much wider range of masses. So we're starting to get a lot more information about those mergers, and we include a lot more. So very quickly, I'm then going to point out the last thing we want to consider, which is the detectability of the gravitational waves from these mergers. So for every merger, we can calculate what the frequency strain signal from the gravitational wave would be, find the peak of that signal. All right. I'm not going to get into details here. There's another undergraduate, Paulina Petrov, who's now a grad student at Vanderbilt. was calculating how long the gravitational waves should be detectable by LISA. Some that will not be detectable at all, some for a few days, some that will be detectable potentially for years. So we've got analysis of that I won't get into here, but come talk to me if you'd like. So here we're plotting the frequency versus strain. And the x-axis will show up in a second. This one's intentional. So here's Astrid, here's TNG. All right? And so you can see TNG 300 has tons more than Astrid does. But the reason is because Astrid was only run to redshift 3, whereas TNG goes to redshift 0. So if we limit TNG to only go down to redshift 3, or go from redshift 3 and higher, it now starts to look quite similar, except there's nothing down here, which we do have here in Astrid. And that's the seed mass issue. So then, if we take Astrid and limit it to only be the same mass scale as TNG, we get this. And so here you can see they're in very close agreement. The difference is most of these are just cut out when I put in a strict mass cut, whereas TNG pretty much just sort of shifts most of them up to there, because that's where they're getting seeded. And we can also look at the masses involved in these mergers. So this is M1 versus M2, just the two masses involved in the merger. And this is color-coded by the signal-to-noise ratio that LISA will detect. And so that's TNG, and then here's Astrid. So you can see, again, very similar behavior in the scales where they both exist. But with Astrid, we can now see, instead of the peak being basically when they're getting seeded in something like TNG and a lot of other simulations, here we're actually able to see the peak here, and our seed mass extends down to below the peak signal. So the strongest signals are well resolved with the Astrid simulation. And we can directly look at the signal-to-noise ratio distribution that will come in. And if we just take the raw data from both simulations, we get this. And again, we see a lot in Astrid that isn't there in TNG. And if we cut out everything that's close to the seed mass in TNG, then we get this close agreement between the two simulations. Very good here. You'll notice Astrid drops off. That's because TNG is growing them more efficiently, and the more massive black holes have lower SNR in LISA. But the nice thing is this dotted line we can put in, that's in Astrid, that's still above the Astrid seed limit, but is below the TNG seed mass. And so there we see there is this large number of very high SNR signals that should come in to LISA. So I'll end there and point out, just sort of threw a lot of information at you, but the key thing here is we are starting to be able to make very accurate predictions for what LISA should detect, what PTAs should detect, but especially for LISA, it's really important to include the low mass end. You have to seed with low masses. And including dynamical friction is crucial because it affects both when mergers take place, how many take place, and what the merging masses are. So I will end there, but also point out there's another paper that I didn't have time to discuss here, but using the same simulation that's then looking at black hole pairs, looking for dual and offset AGN, and how they're triggered by mergers. That went on archive 2 weeks ago, I think. So I'd recommend you take a look at that as well. All right, thank you.
Thank you, Colin. We have time for a question while our next speaker sets up.
Colin, thanks for that great talk. So in TNG, there was this problem where even though the black hole masses for the quenched galaxies were roughly right, compared to observations, the black hole masses for the star-forming galaxies were about an order of magnitude too massive. And I'm wondering, since Astrid has less efficient black hole growth, did you check that that's been solved in Astrid?
So we're looking at, there's a lot that we're still looking, the simulation's still running, so, basically this end where we have much lower masses, I think there's a good chance it will. Various people are all looking into growth at the moment, so we're trying to look at the details of exactly what changes the growth models and how much the mergers come into play versus the gas accretion and everything, and we're tracking all of the black holes back to when they were seeded and sort of doing an analysis of the growth behavior, but that's still in progress.
This should be divided between quenched and star-forming.
Yes, but I'm saying the first thing is just to look at what the growth is like, and that's the stage I'm at the moment. And then looking at correlating with the host galaxies will come right after that.
I see one more question back here.
Do you want this?
Hi, thank you for such a nice talk. So my question is, at scales larger than kiloparsec or few kiloparsec, I understand that the dynamical friction prescription probably is trustworthy and you can get the timescales right. And also when the black holes are at a separation of 50 or so Schwarzschild radii, when at their very small scale, then gravitational wave prescription is very well determined and you can get the time scale. But in the intermediate regime, when you're transitioning from the dynamical friction to gravitational wave scale, and where there are nucleus, star cluster, and everything controlling the multi-body dynamics, how trustworthy is that time scale measurement, and that will really impact the rates that you calculate?
Short answer is yes. You're correct that that's going to be significant, and it's below the sort of simulation resolution. Around it. So yeah. So I said that this includes dynamical friction, and it does, right? But it doesn't go to infinite resolution, right? So we've also got so Nyanyi Chen has a paper that was looking at some of these merger rates, and she did some sort of post-processing merger rates after the dynamical friction simulation that included hardening times and other things. So there has been some work. That was a 2022 paper, so it came out this year. So there's some more details there, but yes, it's definitely something that needs to be looked at. It's one of those things that's sort of push what we can get in the simulation as far as we can, and then we have to do some calculations after that.
Okay, let's thank Colin again.